Hello, everyone, and welcome from Data Center Knowledge. My name is Alan Howard. I'm a data center market analyst at Omdia, which is a sister brand to Data Center Knowledge here at Informatech. Today, I'm joined by Nigel Gore, who oversees global offerings and high density and liquid cooling at Vertiv. Welcome, Nigel, and thanks for spending some time with us.
Thanks, Adam. Good to speak to you.
So today we're talking about liquid cooling. And I think we got to start off. I mean, most cooling in data centers nowadays is air cooled, but air cooling is often uses liquid. So let's define liquid cooling in this context so it's clear to our audience.
Sure. Let me start off by saying that, where we define liquid cooling, we define it by the liquid or the fluid, should we say, that is going directly to the electronic components that are being cooled for the data set, or the heat generating components. So when we say the differentiation of fluid, we're talking about the type of liquid or fluid that is being used to capture the heat, harvest it away from these heat generating components, and send it through the facility for heat rejection. And we differentiate that by two types of fluid: dielectrics and non-dielectrics. A non-dielectric, for example, is water. And we use water. It's a very effective medium for transporting heat. It has a very high heat capture rate. And we take water directly to the hot components. It's typically the CPUs, GPUs, and memory modules in IT components. For communication devices, these are ASICs. And they, because of the conductive nature of water with electricity, we need to insulate it from coming into direct contact with the electronic component. So we use a cold plate, which is a material made out of copper, and it is designed in such a way to effectively allow the water to collect the heat and then transport it outside of the electronic components through the facility, through pumping units, to then externally outside the data center for heat rejection. The other type of liquid cooling is using dielectrics. So these are liquids or fluids that are dielectric by nature, which means they do not conduct electricity and are insulators. So they can effectively come into direct contact with the electronic components. And these are used in a technology called immersion, where the electronic devices are immersed inside tanks or chassis or containers that will then hold not only the liquid, but also the communication or server devices. The heat is conducted directly to the liquid. The liquid is then circulated and heat exchanged, where the liquid is then transported. The heat is then transported outside the facility for heat rejection. So essentially, for liquid cooling, we have two main types of cooling: direct liquid cooling using water-based liquids, and we have immersion, which is using dielectrics. Hope that helps to differentiate it.
It does, and you went into some pretty good detail on the differentiation between direct-to-chip and immersion. If there's anything else you want to add in terms of that differentiation, that would be good. But also maybe talk a little bit about the hurdles that we might want to be aware of for either direct-to-chip or immersion in this context.
Well, I think we recognize that the dominant cooling medium is air. So all data centers today are designed around air cooling. It's not to say that they're not familiar with using liquids in the facility, because we typically have chilled water going into the facility, and these are used for the cooling of computer room air handling units and air conditioning units to provide the cooled air. But what is changing is that in order to effectively remove the heat, we're taking the cooling medium directly to the heat source. So as you do that, the challenge comes for an air-cooled data center to be able to convert to accommodate this new liquid cooling technology. And it's quite disruptive, because you need to, your technology spaces are typically already built out, and they've been designed to manage airflow. Now, to take liquid directly to the servers, you need to put pipework and pumping infrastructure to be able to support this. Not to mention, the any kind of tanks or immersion or immersion chassis or server racks that can accommodate liquid cooling. So we're specifically talking about pumping units and pipework, which means that you need to take an existing data center offline for some time to be able to do that. So one of the hurdles is where to deploy liquid cooling and when, whether it's for a legacy data center or for a new build, where certainly you can design it from the ground up, and therefore factor these type of learnings in when you're actually at point of design.
No, that makes good sense. And I would also assume that if you're building new data centers, that's a consideration to take into account when you're designing the plumbing, is the potential use of direct-to-chip or immersion cooling for your customers. Make sense, right?
That's correct. And we talk regularly to data center consultants around some of the challenges and design parameters that they need to be looking at to prepare and enable for new types of cooling that's coming through. And the reason is that they're seeing the heat density increase in their racks. So we're seeing the overall power load, and as a result, the heat load of these racks increasing, where traditionally for a standard cooling device, it could be in the region of 5 kilowatts, maybe right, increasing to 10 kilowatts. And in those examples, you don't need to, the IT devices that are generating that kind of heat typically don't need any other form of cooling other than air cooling. But we've seen with the advent of artificial intelligence, machine learning, a greater number of devices being necessary to support high performance compute, high performance GPU compute as well. And as a result of the change in application to support these new data-rich features, new IT devices are basically getting more powerful and as a result, hotter. So we're seeing where the rack density traditionally was, 5 to 10 kilowatts for a traditional server. These are increasing to 30, 40, and in some instances planning for 60 kilowatts a server rack.
Yeah, I was going to say at 60 kilowatts, air cooling is just not an option. So I mean, that was going to be my next question: is what's driving adoption of liquid cooling? But I think you pretty much covered all that. It's a combination of applications and the advanced hardware required to do that.
I think that's true. We are seeing that increased heat density. Now, there are HPC systems that can go up to and beyond 100 kilowatts. We've seen examples of 160 kilowatt racks. And these are quite specific targeted racks where they've been used for supercompute. If you look at the top 10 supercomputers out there in the world today, they do typically, you'll find a number of them deploying some form of liquid cooling. It's typically direct-to-chip liquid cooling because of the density of the compute that they are trying to achieve. So what we're seeing here in terms of the applications is that there are a proliferation of higher performance compute devices going into more applications, and as a result, we're seeing growth for these compute devices, which is resulting in the higher density racks, these higher kilowatt consuming racks. So that's essentially where we're seeing it happen. And there's a combination around IT chip design, and that's being integrated into server design. As the fabrication processes for these chips is enabling to add more transistors, more transistors per square centimeter, it is resulting a key focus on the cooling. And you mentioned air cooling. You cannot across what we typically can see is within a 2U form factor, you can get several kilowatts of compute, and in order to try and support that with air cooling, you just cannot get sufficient airflow So essentially what we're saying is with some of these new compute devices, the only option is liquid cooling.
Yeah, no, that makes complete sense. In fact, on the team that I work with and the research that we do, the growth of liquid cooling it's significant in terms of where it's at now and where we expect it to be in the next few years for all the various reasons you were just talking about. So let's talk for a minute about the economics of liquid cooling and total cost of ownership. How can you characterize that for us?
I think the first part we got to look at is where is liquid cooling being deployed? So we did mention it around these higher density racks. So what we see, and you can see in the recent news, NVIDIA has been announcing their new GPUs that are being launched to support the A100 GPUs.
Mm-hmm.
This was done in Computex, I think a week before last, and that is, if you look at the announcements, there are liquid cooling or dedicated liquid cooling SKUs only. We're also seeing from Intel similar announcements around some of their new their chips and servers supporting this. So whilst economics is a key factor, the first impact that the data center will have is they won't be able to support these applications. So there is certainly a first mover advantage that it's basically to be able to support these applications. Now there are additional benefits that augment liquid cooling, and we can harness these for extending liquid cooling into other systems. And why that is that you're able to operate the facility at an elevated temperature because we're taking the cooling medium directly to the heat source. We are removing a lot of inefficiencies around the cooling capabilities of the system. And by doing that, we can be more precise and we can remove some of the associated complexities in moving air around the facility. So we do look at a simplification around some of the data center design. And with that simplification, you do get operational efficiencies. Plus the addition that you're operating at elevated temperatures, you can save on operational expenses around energy efficiency. You will be reducing the demand on fans, as an example. Mm-hmm. So that will have a power saving. And one can look at the percentage of power that's taken up by a fan, and you can discount that. So you do get some benefits around the power reduction. So power reduction, energy efficiencies relating to operating at elevated temperatures, as well as the overall complexity of the mechanical architecture that's within the facility can also be explored as possible economic drivers for liquid cooling.
That makes good sense. And so at this point, walk me through how Vertiv can help your customers and the kind of product solutions that you're offering. It's not a new industry, but it's recently it's been in sort of a transition to become more mainstream, and a company like Vertiv has to be in the middle of it.
Exactly. And you bring up all the core competencies which Vertiv is renowned for. Our global footprint around service and maintenance means that customers are assured with best practices for deploying these types of technologies. We have thermal products to be able to support the delivery of liquid cooling products, liquid cooling services into the facility, which include heat rejection, the liquid transportation, so we're talking about pumping units, as well as rack architectures to support the distribution of the liquids as well. Plus, our power teams have dedicated power distribution units to be able to support these increased power hungry racks. You need the entire ecosystem of architectures of components to be able to support moving to these higher density racks. So it's not just about deploying liquid cooling, but it's the augmented services that come with it, power as well as the compute and the thermal architecture, and then the housings for it, the racks and the UPS systems to make sure that they backed up. And if you look across the Vertiv portfolio, we have a solution focused around these solutions.
The whole package, in other words.
Correct.
Correct. Yeah. No, good overview, and it's been a great conversation. I've learned a lot here, but any words of advice for our viewers and listeners, or any final thoughts you'd like to share?
Thanks for that. I think the key thing is that applying liquid cooling needs to be done with some thought. You do need to be able to study and identify where your requirements will be for your thermal architecture. There are a number of fragmented technologies that are available for liquid cooling, but certainly choosing the right one that's fit for purpose is going to be paramount. So we are available. Contact your Vertiv sales team to speak to them, and we can assist either the data center operator or the data center consultant to guide through some of the best practices that could be considered to make sure they can future-proof their data centers for liquid cooling. Thank you.
Well, Nigel, thank you so much. It was great talking to you today. Appreciate your being here.
Thank you.
And
good day
from both Data Center Knowledge and Vertiv, thank you everyone for tuning in and listening.